Okay, so then I'll do the introduction. So, good
Perfect.
afternoon, everyone. It's my pleasure to introduce Maximilian Diehl from Chalmers University of Technology. So, the first in this kind of batch of last year PhD student seminars. And the title is Explainable and Interpretable Decision Making for Robots. So, that's interesting for a lot of us, I think. So Maximilian is, as I said, at Chalmers, supervised by Karin Ramirez Amaro, and he got his bachelor and master's degrees from the Technical University of Munich. So please, Maximilian, take it away.
Awesome. Thank you very much for the kind introduction. Since you all know now who I am, I'll jump directly to the content. So as you explained, I'm working on explainable and interpretable decision making for robots. I always like to show this video at the beginning, which I think summarizes really nicely what and how we envision future robots to be like. So we envision these robots to be parts of our daily lives, help us with cooking or taking over some of these daunting tasks, such as cleaning or doing the laundry for us. Unfortunately, as many of you who work with robots might know, acting in these human environments, which are very unstructured, dynamic, and also varied. So every kitchen, for example, might be different, is very challenging for robots. And so it's inevitable that they will fail. In fact, failure is not only I think, a feature that only concerns robots. Also, we humans struggle sometimes. We might accidentally slip a glass of water or, have problems, spill some milk while preparing cereals. And so it's very important that we equip robots with methods that allow them to deal and handle failures effectively. At the same time, there is a new problem coming in, which is the fact that these robots are now supposed to really work and operate in these human environments, which are very personal, very private, and for particularly these non-expert users who don't work with robots on a daily basis, it's going to be very difficult to understand what's going on and understand why robots fail. And so explainability and interpretability becomes very important, particularly when it comes to dealing with failures. And it's been shown, for example, that this is important for increased trust and acceptance of these robots, as well as can help with diagnosis. So, for example, if a robot actually needs help to recover from the failure and needs human support for that. Um, the goals that I have been working on during my PhD so far are really methods that deal with failures, and particularly want to be able to explain failures, predict and prevent future failures, as well as enable humans to support if need be. And the kind of objectives that I set for myself in order to make it explainable are summarized in the following bullet points. So particularly, I looked in literature from psychology or cognitive science, and they suggest that humans, when they explain and provide explanations, they often use contrastive, selective failure explanations, and they avoid probabilities. So that's important. Another aspect that, is I think quite obvious is if we could use human understandable symbols for the decision making of the process, then also we could enable robots to be more explainable. And finally, a kind of emerging topic, I would say, that has been gained some traction over the last years is causality. And so obviously for us humans, causality is such an important aspect of reasoning and helps us to understand why failures have occurred, but also help us to understand what we should actually change to, for example, prevent failures in the future. And I think this is also an important aspect, could be an important aspect for robots. And so out of these objectives and goals, I first started to look into failures that happen during the task execution. And the first research question that I tried to address is, well, how can we even obtain these causal models to model our tasks? And then based on these causal models, how can we provide explanations which are contrastive and selective? And how can we use these causal models to predict and prevent future failures? And on the other hand, regarding human support, that's obviously quite an open and field, and there's a lot of possibilities. I particularly focus on failures during task planning. So typically before a robot might execute a task such as setting the table, which requires a long sequence of actions, it's good if it had the capability to plan ahead. What are the actions that it actually needs to execute? But what if the robot is not able to find a plan because it is missing particular actions that prevent him from finding a plan? And so in that case, we propose that we can overcome this through learning from demonstration. So by watching humans demonstrating the task or the missing actions. And now I'm going to go through all of these research questions step by step, starting with how do we actually learn, or how can we learn and obtain causal models? So we propose this three-step approach consisting first of variable identification. So essentially, in the beginning, we need to somehow define a model of our tasks. So we need to define a set of variables that can describe how the environment or how the task works. So for example, for the task of stacking cubes, we use variables such as drop offset, X and Y offset, as well as the cube color. And importantly, we also need to include a variable which describes the task outcome. So in this case, on top. Does this cube land on top of the other one? Here's another example of a different task where we try to drop the sphere into one of the containers. Again, the offset becomes important, but we have additional variables such as that describe the container, such as curvature, size, height, and color. And so in this case, the inside variable is the one that will determine if the task was successful or not. And so you can understand this kind of as a pre-selection of variables. They don't always, all of them necessarily have to be causally relevant, but we're going to keep track of them and measure them throughout our experiments. And then to actually obtain the structure, we first collected a bunch of experiments in a simulator. We used Unity for that case. And now we first want to obtain the structure. So going from this unstructured set of variables, we try to learn a directed acyclic graph. I should also mention that the kind of causal model we utilize here is a causal Bayesian network. And there's a lot of variables, a lot of methods out there that can do that. We typically use Cron Shrink and MPC, which I think are quite classical algorithms. There's others that you can use as well, depending on, for example, what are additional assumptions you can make about the data. For example, are they linear dependent? Once we have the structure, then we can also estimate the parameters. So this is a probabilistic representation of the task. In particular, we want to estimate the conditional probability distribution of a node given dependent on its parents. And there's classical methods such as maximum likelihood or Bayesian estimation. And particularly interesting is, of course, the outcome variable, such as on top, because that allows us to estimate the success probability given different values for the parents. Another thing that's important to understand is, for the sake of the structural learning, we discretize all of our variables. So there are some variables which are, of course, naturally discrete. For example, on top is a Boolean, true or false. But other variables like the offsets, they were sampled from a continuous distribution. And so we discretize them into intervals, so indicated by y1, y2, and so on, which always stands for a particular offset interval. And now moving on to explanations, just given what we already have now, we could provide some sort of explanation based on probabilities. For example, in this case here, we could explain that the robot had to fail because the success chance was only 40%. But again, that's not how we want these explanations to look like. We want them to be contrastive. And we propose to generate this contrastiveness by conducting a search procedure to find the closest variable values which are likely going to succeed given our causal model. So in other words, we start with the failure parameterization. So for example, x1, y2, z1. And then we change one variable value at a time. So here we jump from x1 to x2, y2 to y1, and so on until we find the closest parameterization, which, given our causal model, would have likely led to a success. And then we only look at the subset of variables which have actually changed. So Z, for example, here did not change its value. So we don't incorporate it into the explanation. We only look at the variables that have changed and then set in contrast the variables that have changed. So x1 instead of x2, y2 instead of y3. And if we put some interpretation, what these variables actually represent, we can provide an explanation such as I stack the upper cube too far to the left and too far to the front of the goal cube. Now, the next step was how can we predict and prevent future failures or errors? And so to illustrate, let's look at this slightly more advanced stacking example where now we want to stack 3 cubes on top of each other. And you can see here that this first cube was stacked very far to the right, but actually it didn't immediately lead to a failure. The failure only happened later when we stacked that final cube. So we wanted to be able to also detect basically the causes for these failures. And we, again, started with learning a causal model. In this case, this represents all the 3 tasks, all the 3 stacking tasks at one model. So you can see with increasing height, we also depend on the past. And that essentially, then from that point, starting with the parameterization here, we again conducted this breadth-first search procedure to find what is the cause, the underlying cause. And the model suggested that it was by realigning this initial cube, we will actually be able to fix the error and stack the whole pile correctly. Yeah, to show some results, this is based on simulation. So we found with no correction, we had around 80% failures, which got greatly reduced by using this stacking model. The only issue is that the more complex the models get, in particular, the more inputs we have. So here, for example, you have 7 or 8 inputs, the more data we need to learn these models. So I think here we used around 1 million data samples, which is quite a lot, obviously. And so we also compared that by using a simpler model, the one-stack model, which also helped us to reduce the failures, but was not as good. So it's kind of a trade-off. But at the same time, that also led us to investigate more ways how we can actually reduce the number of samples that are required to obtain these causal models. So we jump back to our research question 1. And one of the ideas we had was, why don't we try to obtain and use these like prior information from the simpler models, such as here the single stack, and try to apply that to our 2-stack model. So really the idea is, again, to illustrate, the problem is we have an explosion in data requirement. So for example, by having 2 times the amount of incoming edges for this parameter estimation, we have a quadratic increase in the number of samples we need, because there's just so many more possible combinations of parameters that we need to estimate. And so here the idea was to use the semantic similarity of these models to do this transfer. So in this case, x and y are variables that appear in this stacking task, but also in this stacking task. And the cool thing is, it might also be possible to transfer to completely new task. For example, x and y is also relevant for this sphere dropping task. And I would argue that actually many manipulation tasks would have this x and y offset as part of a relevant variables. And so what we did is we did parameter estimation using Bayesian estimator. So that one combines the priors with data on the new task, and maximum likelihood estimation, which always learns the data just from scratch on the new task only. So it doesn't include any prior information from possibly simpler task. And then we compared the distance between the estimation and the ground truth, and also used these estimates as input for the failure prevention method that I've introduced in the previous slides. And the outcome here was that definitely priors help robots making better decisions when predicting and preventing task execution failures. So just having this this prior helped to up to 50%, led to 50% fewer task execution failures. Particularly, we saw the advantage in the kind of zero-shot transfer case, or when there was only a very limited amount of data. For example, 1 or 2 samples per parameter that we tried to estimate. However, we also saw that this once we actually do have enough data, it's actually probably better to not include the prior, because the prior will kind of slow down the convergence towards the truth values once we start having enough data samples. Okay, and so that was one of the experiments, or one of the directions we did in order to reduce find methods to reduce the data requirement. We also recently started to work on a human-robot interaction scenario. So let me just introduce the task first. So the idea is, imagine you're in a supermarket and you're looking for a specific product, you don't know where it is. Maybe in the future you will be able to ask a robot and that robot will guide you. So we call it a robot guiding task. And so we use a data set for that investigation, which was already existent, where they collected data from humans in a virtual reality environment following the robot to the goal. And here specifically, the task was, we wanted to predict how the human is perceiving the performance of the robot, which was measured in terms of competence. So how competent does the human find or evaluate the robot movements? And the interesting aspect about this prediction task was that the data samples that are available here, they essentially provide a time series type of data over a specific sequence time, in this case, 8 seconds, and then observing the robot behavior, the environment, what the human does over 8 seconds. Based on this data, we should predict what is the competence or what is the perceived intention of the robot. And that was, for several reasons, very interesting, because it forced us to think about how we can combine different types of data into the graph. So first of all, we could already deal with this naturally discrete and binary and continuous data, but now we also have this time series data. And so the first question was, how can we include that into the similar graph structure? And what we did in the end was we clustered the data. So we generated, so here you can see an example of the robot position trajectory, always starting from where it is currently. And then, for example, these kind of trajectories here, they denote that the distance is decreasing. So the robot is moving towards the goal. And the ones up here, they denote that the robot is moving away from the goal. So the distance is increasing. And of course, we have time series data, but through clustering, we sort of discretize them. And then we can also include them into our graph. The other problem here, even though this data set had around 3,000 samples, which is big for HRI applications, it wasn't big enough to actually learn the graph. So we handcrafted it. And I think that's also actually nice, because that shows that the construction of these causal models can also very easily include expert knowledge. And so in this case, we only constructed the graph by hand, but actually the parameter estimation was then done automatically using the available data. So you can very easily combine these kind of different approaches. Just to show you some results. So this is ongoing work. It's unpublished right now. So, but I still think the results are pretty nice. We could see, for example, that even though this was quite a simple model, it didn't, for example, include information about the environment. We had equally good or even better prediction than other state-of-the-art methods, comparable methods, which the best methods for this particular use case, which was a random forest. And also we were able to apply this contrastive search procedure to, once we predict a low competent robot behavior, search for better behaviors. So in this case, we applied the search obviously on the clusters, for example, and then we kind of, to illustrate the output, we directly applied the newly obtained clusters with the behavior which is predicted to lead to high competent behaviors to the robot. So here in this little video, you can see several things. So you can see up here the goal in green. So this is where the robot should navigate towards. The environment here is free, and we also have some obstacles, which is indicated by the black bits here. We have the human follower in red, and the original robot behavior is illustrated by this blue line, blue arrow, and the newly obtained behavior, so the one which is predicted to increase the competence, is this pink arrow here. And there's also some other pedestrians which were randomly automatically controlled. So in the first pass, let's just focus on the blue arrow, which is the original robot behavior. And you can see that the robot is just moving a little bit forward, and it just waits and stands. And now the newly obtained counterfactual behavior of the pink arrow, you can see it's slightly rotating towards the goal and then starts to move into that direction. So yeah, we were really happy with that outcome. Cool. So now I finished with the section about failures during task execution. Let's now jump to the second part of this talk, where I'm going to talk about failures during task planning. And before I'm going into more detail, I just want to give a short background on automated planning, which is really the underlying framework that we use to perform the planning. So the idea is to plan ahead how to solve a task before actual execution, and we're using descriptive models which not focus so much on the actual how the task is executed or how an action is executed, but describes what's happening in terms of symbolic variables. So typically a so-called planning domain consists of a state space, which is basically a set of variables or Boolean facts about the environment. For example, on top, in hand, graspable. So in this example here on the left, the blue cube is, for example, on top of table, and the red cube is in hand of the robot. And then this set of states or this set of symbols is also used to define actions, which in this context are called planning operators, in terms of preconditions and effects. So the precondition essentially denote what has to be true in order to execute the action, and then the effects denote what change happened in the environment by executing that action. So, for example, before stacking, the cube has to be in hand of the robot and not on top of that other cube. Then through executing the stacking action, now the cube will be on top of the new cube, so red on top of yellow, and the cube is not in hand anymore. So this is how we build up and describe the environment and build up a set of actions that enable the agent to act on its environment. And delta is just the transition function that happens when you chain different actions. So then a planning problem is now also including an initial state and a goal. This initial state and goal are again defined through this set of symbols. Yeah, for example, all of the cubes are on top of the table, and this is our goal configuration that we want to reach. And then we can parse all of this information, initial state, goal, our set of actions, and so on, into a planner, such as fast downward, and that hopefully, if everything goes right, this will output a action plan that enables this transition. So we get a plan pi, which enables the robot, which consists of these actions A1 to N, which enable the robot to go from initial state to goal state. And now we define a failure as when there is no plan that allows to achieve this transition. And again, right now we assume that we did an exhaustive search, and the reason really is that some actions are missing in that action state, or some operators are missing, so we cannot actually achieve this transition. And the way to overcome this failure now is through learning from demonstration. So we want a human in the loop who is demonstrating the task. And so challenge one is, how do we translate that demonstration into operators that we can add onto the current action space, so then we can actually enable and achieve a plan. And so we developed a system where we can collect demonstration in a virtual reality environment. And then the first problem is that these demonstrations are sort of just a sequence of state descriptions. The first challenge is how do we actually segment them into timely intervals, so we can understand when one particular activity starts and when it ends. And so for that, we rely on prior work from my supervisor, from Karin, who came up with this activity recognition system. So we focus on the hand movements and we describe the hand activities with very simple features. Hand move, do we act on an object? Is there an act in hand? And then based on this decision tree, we can, or based on this table, we can classify the current hand state at each time point into one of these high-level activities: idle, reach, take, put, or stack. And so that seems quite simple, but actually we found that this set of actions is very easy to generalize. So actually we used exactly that same table basically to classify the hand activities over a wide range of different tasks. And so this is really to understand when a specific activity starts and when it ends. And now we also need to connect these hand activities to changes in environment, of course. For example, a change in on top variable if a cube is stacked on top of another one. And so we generate these planning operators by always looking, or by the preconditions. So every time we have a state transition, activity transition here, we generate a new planning operator, and the preconditions are based on the last state of that previous action, and then the end, or the effects are based on the last state of the current activity. Awesome. And then if everything goes well, that will enable us to now generate plan to these new activities. Another problem that we tackled is, and so this is, I think, many learning from demonstration methods mainly focus on how can we extract new knowledge from these demonstrations. But actually, what is required is usually a demonstration of either the complete task, or it is kind of assumed that the user who's using these learning from demonstration methods already has quite a good understanding of what actions the robot are actually missing. And so this is also something we wanted to change, so we can in the future also enable these non-expert users, because redemonstrating the whole task can get really annoying. Imagine you were teaching the robot how to set the table, but now just a small detail has changed in the environment. For example, this chair was now suddenly moved in front of the drawer. So it's just a single action really that has to be redemonstrated. But yeah, the robot still won't be able to achieve its goal. And so to help out with that and to bring down the demonstration burden, we we worked on guided demonstrations. So the idea is we, through common neutral search, we try to change the initial state. So we try to add or remove facts to that initial state until we find a new state, which we termed excuse state, from which now all the existing knowledge is enough, such that the robot can find the goal. And since we use semantic action descriptions, we then only need to somehow communicate this state change that we need to the user. So for example, here, the change that was required was, can you show me how to reach a state where the pink draw is clear? And actually, we just put that instruction sort of directly in the virtual reality environment, and that allowed us to then get a demonstration only of the missing pieces. And we show that this actually greatly reduced the demonstration burden on the users. We also worked on a multi-agent, an extension to multi-agent planning. So most of the learning from demonstration methods actually focus on single agent, but there are some additional requirements that have to be met or have to be encoded during the learning to also enable correct plans. Just to show you some examples, the notion of shared spaces becomes important. That has to be encoded in the learning process. So for example, a certain spot here cannot be accessed by two agents. In this case, we refer to the right and left arm as separate agents at the same time. or some actions, they actually have to be scheduled in parallel to be successful. So for example, to open a little jar here, we have to execute two actions in parallel. And again, this has to be explicitly encoded into the planning operator when we learn it. So I don't have enough time to go into detail, but if you're interested, this is the paper, was recently published at CASE conference. Cool. So now I'm already at the end. So I just want to provide a quick conclusion. So what I've shown you are different methods that should make dealing with failures more explainable and interpretable, particularly by focusing on contrastive selective failure explanations, human understandable symbols, and using causal models. So in the first part, I've talked about failures during task executions. I explained to you how different methods to obtain causal models, either from simulation or with some tricks, for example, through priors or even human input, human expert knowledge, then how to use this to provide explanations and predict and prevent future failures. And in the second part of my talk, I focused on failures during task planning, where we utilize a human in the loop, a human demonstrator to learn the missing subtasks or tasks so that the robot can succeed with his task plan. Yeah, thank you very much for your attention.
Thank you, Maximilian. So let's have a virtual applause for this presentation. So questions. So either raise your hand or just speak out.
All right, I have a question. So my name is Erik Söderberg from Saab Dynamics. A question about really the concept of explainability or explainable behavior. I see, it seems to me that there's a difference between like real-time or runtime explainability with reference to some human that wants to understand or interpret the behavior, as opposed to like post hoc explainable or given full information. Is it explainable or interpretable in principle? Do you think about these questions, and does that map onto your work in any way?
I think probably we mainly focus on the post hoc because really the goal was to provide explanations after the failures occurred. So I would argue that probably that was more the post hoc part. We haven't looked into detail regarding the other aspects. Maybe you're referring to behavior that is explainable in some fashion. So we haven't looked into that.
Okay, thank you.
More questions? Yes, go ahead, Maria.
Yeah, sorry, I didn't find this icon. Hi, everyone, Maria here. Hey, Maximilian, nice presentation. Thank you. Interesting topic. I wanted to ask you about the concept of these contrastive explanations. Do you define these contrastive explanations a little bit like maybe the machine learning feel that there were how much do I have to change the input parameters to change the outcome, and then the minimal changes will be like the concept or the content of your explanation. So if you would move the cube, I think you show some cubes, like it's a little bit more, then you would have done it right. Is that how people use contrastive explanations? I mean, because I think this is a bit simplistic. I mean, sometimes you will not explain, okay, the robot did it wrong because it's just 1 centimeter head, but instead they say, the robot didn't, I don't know, knew how to place this and so on. Is this way of seeing contrastive explanations from this machine learning world the way that resembles how we human use contrastive or counterfactual explanations?
Yeah, that's a good question. How I see it is one way how humans use it, but also how do we actually implement it?
Yeah, that is.
And definitely, from my eyes, it made a lot of sense to do it in that fashion, because we can see the failure and I mean, there might be also different alternatives that can actually lead to the success, right? So, but we have to come up with some way of generating that contrast.
Yeah.
That's it not necessarily the only one that we can generate. Even on that level, right? We might be able to find, a different set of explanations also with the same amount of failures, just at a later stage, which might lead to a different explanation. But yeah, I think from an implementation point of view, being able to generate, like, there's many possibilities, many possible counterfactual worlds, if you will.
Yeah.
But yeah, you
And
somehow
this is what is hard, because you say also that your explanation should be selective, you think. And I think humans were quite good selecting the most maybe important reason from our perspective. And sometimes
Yeah,
it doesn't
definitely.
coincide with this machine learning change in a
No, I definitely agree. Like, we humans are extremely good at discerning the actual important variables. Yeah, so it's
okay.
a challenge.
Thank you. Thank you. Thank you.
Thank you. More questions?
Hi. I'm Suresh. I'm from Carnegie Mellon University in the US, and I had a question. A great presentation, by the way. Really interesting talk. And I had a question about personalization in explainability, particularly in, like, like human robot interaction applications. Like, something that's intuitive or explainable to one person might not be understandable to the other person. So, like, how do you, I guess, like, what are your thoughts on, like, this personalization of this explanation, and how do you think this approach that you're using can be personalized in the future?
Yeah, it's an excellent question. Definitely I guess the level of explanation that we provide, ideally we can adopt it to the user. So one way of changing the way, the level of explanation, if you will, is changing the state space, or choosing a different set of variables. That could be one way. Another way that unfortunately I didn't, or another idea would be also to adopt this search procedure. So maybe some variables are more important for a given set of users. So also adapting the search procedure, prioritizing some variables over another could be one way of adapting and potentially personalizing, I think, that the type of explanation we obtain in the end.
Okay, great. Thanks.
That makes sense.
Thank you. More questions?
I have another question.
Sure.
So there's a difference between like achieving explainability either through making the decisions or making decisions that are easier to explain, right? And maybe better or more optimal. Or you could just become better at explaining the same actions, for example, by introducing some new representation or way of inspecting the actions. And do you see yourself tackling, I guess, both, right?
Yeah, that's a very interesting thought. So you're saying, maybe in the planning process or in future steps, also prioritizing actions which are more easily explainable. Yeah, we haven't looked into that so far, but that's definitely interesting. Can you again repeat the second part? There was a second part to the question.
Yeah. So what I'm saying is either you could make decisions that are easier to explain, and that may or may not be like better decisions, right? It could be that a worse decision is easier to explain in theory. But okay, that's the first part. And the second part is you could, given the same actions, you could like become better at explaining that by introducing some new representation or
yeah. This is interesting. So actually adapting maybe the state space in order to could even be related to personalization. So that's definitely interesting. We kind of in that process. Yeah, for that for that example I mentioned about this one here, where we for this part here. So when we developed that model here, actually I was the expert here and I modeled that graph, but we also conducted some user study to see if, for example, users would generally agree with this model, or if they would use other types of variables, maybe additionally, which obviously impacts the type of explanation we can obtain. And so I think, yeah, by basically changing the model, adding variables, that could be potentially achieved. And so, yeah, I think there's also potential to improve these models with additional inputs, however we may obtain them.
All right, thank you. Very interesting.
Thank you. Lots of good questions here. Any more? Okay, so let's thank the speaker again.
Thank you very much.
Yeah, some virtual hand signs there. So just next week, we're going to have 2 exciting presentations, one on human-centric specification frameworks for connected vehicles, and the other is for autonomous control of bicycles. So sounds pretty exciting to me. Okay, thanks for attending, and goodbye.